We're going to start Chapter 7, and Chapter 7 is the beginning of our last unit this semester, and we're looking at inference and making inferences about a population based on a sample. So this first section, we're just looking at several definitions that relate to when we take a survey. So imagine when we poll people, say on who they're going to vote for or their opinion on a particular issue. This is what we're talking about in this section. So some different terminology that I want you to be familiar with. So filling in this first box here, that first blank there, I'm using new software here, so let's see if my handwriting looks a little bit better. Oops, let's turn the pen on. So a population is the first term. We've used this term before, and I know you've heard this in other classes, but a population basically refers to a group that we're interested in studying, and it's the entire group. It can be people, it can be objects, it can be animals, but the entire group is your population. And then if we do a calculation on that population and we come up with some numerical value, that is called a parameter. So a parameter is some sort of numerical value that represents some aspect that we're interested in studying about that population. It could be the proportion of people who say they're going to vote for a candidate. It could be a population mean. It could be a population standard deviation. But any numerical measurement, we call that a parameter if it's based on the population. The next term here is called a census. So a census is a survey which measures every member of the population. I know you've heard the term census. We just did a census last year in 2020 in the United States. We do a census every 10 years. So a census is where we attempt to measure every person in the population. We try to go out and gather data on every single person in the population. Generally, that's very hard to do. So instead of collecting a census, what we do instead is we take a sample. So that's the next term here. A sample is a collection of people or objects that is taken from the population. I like to think of a sample as a subset of the population. So if our population was all students at Flagler College, a sample of that population might be just all the students that are taking statistics. That could be a sample of the entire population. So some subset is going to be your sample. And then if we do a measurement on that sample and calculate a particular value, that is called a statistic. So a statistic is a numerical characteristic that we measure on that sample. It could be the sample mean. It could be a sample proportion, a sample standard deviation. Anything that we measure on the sample we call a statistic. It is sometimes called an estimator. So you may hear us use that term, an estimator. And the results, the numerical results, are sometimes called an estimate. So we estimate characteristics about the population based on an estimator or a statistic that we calculate from the sample. So let's do a couple quick examples here. Data is gathered on the heights of all NBA basketball players. The mean data is calculated. So all NBA basketball players would be our population. So the first thing you might be able to do is identify your population. And then the mean that we calculate on that population is an example of a parameter. So remember, the P's go together. It's a good way to remember that. So any measurement on the population that we compute is called the parameter. A researcher is interested in studying the heights of American women. So she takes a random sample of 1,500 women and finds the mean height of the sample is 63.6 inches. So the 1,500 women is our sample. And then the mean that we calculated directly from the sample, only using the sample, that mean that we calculated is an example of a statistic. So the statistic is the sample mean that we calculated. The researcher may estimate that the population proportion for all American women is 63.6 inches tall. So she's going to use her sample statistic to make an estimate about the population. So statistical inference is what we're using for the rest of the course here. Statistical inference is a big topic in research. We think about when we looked at vaccine data, when we researched COVID vaccines, we pulled samples from the population and we used those samples and the data we calculated on those samples to make an inference of how, for example, the vaccine would perform in the general population. So this whole idea of pulling a sample and making inferences to a general population is called statistical inference. So it's a huge topic in statistics. And in my opinion, is one of the most important topics we can study. So statistical inference is the art and science of drawing conclusions about the population based on what we see in our samples. It always involves some level of uncertainty because we can't go out and measure the entire population. I can't test everybody for the COVID vaccine. I can only test a few people, and so that's our sample, and we make inferences based on that sample. So there's always a level of uncertainty when we do this. An important component of statistical inference is the ability to measure. So measuring the uncertainty, and we'll get into that a little bit more in a few minutes. And actually in the next section, we'll talk a little bit more about what we mean by measuring the uncertainty. So a quick example here. In a January 2015 poll, a report stated that 37% of Americans believed that genetically modified foods were safe to eat. This was based on a survey of 2002 American adults. So this is a good question here. I would expect you to be able to answer. Be sure you can identify who your population is, who your sample is, what is our parameter, and what is our statistic. So the population is whoever you're interested in studying. In this case, we're interested in studying all American adults. Sorry, it's getting a little bit messy. All American adults. The sample is the 2002 that we surveyed. So the 2002 people that we asked their opinion of, that's our sample. What is the parameter of interest? So the parameter that we're interested in studying is the percent of adults, really American adults, who think, so what did we ask them? We asked them if they thought genetically modified foods were safe to eat. So we're interested in looking at the percent of adults who think GMOs are safe to eat. Okay. The idea here is we can't possibly go out and ask every single American their opinion, every American adult their opinion on GMOs. So what we have to do is we have to pull a sample and see what their opinion is, and we use that to make the inference to all Americans. The statistic is whatever it is we calculated from that sample. So we calculated that 37% of our sample said they thought GMOs were safe. So our statistic is going to be the 37% from the sample. So the 37% of our sample who thought GMOs were safe is what we're going to say is our statistic, because it's a calculation we did on the sample. So a couple of things about statistics versus parameters. So statistics are always known. Anytime we collect data, we know what the statistic is because the statistic comes directly from the sample that we collect. So we always know what the statistic is. The difference, though, is that parameters are typically unknown. They can always be estimated with the statistics, but usually we don't know what the parameter is. If the parameter is the percentage of all American adults who think GMOs are safe, like I said, we can't ask every single American adult their opinion on GMOs. So parameters are typically unknown. Statistics are always known based on our sample. There are times when we might know the parameter if we have information about the entire population. For example, the NBA players back here, the parameter was the mean height of all NBA basketball players. Well, I do have records on every height, for the height of every NBA basketball player. We do have that information. So in that case, that is an example where the parameter is known. But most of the time, if your population is something large, like all American adults, your parameter is probably going to be unknown. So it really just depends on who your population is. A couple of notational things you need to be familiar with. We're going to use these notations quite a bit through the rest of the chapter. And actually, some of this we've already done. So the sample mean, we did that earlier in the course. Remember that the sample mean was X bar, whereas the population mean, we used mu. And remember in chapter 6, I noted that difference. Mu we used for the population mean, X bar we used for the sample mean. Sample standard deviation, earlier in the course, it was lowercase s. If we're talking about the population, remember the standard deviation is sigma. Remember we used that in chapter 6. Variance we haven't done much with in this course, and we won't do much with it in this section, but the variance is the square of the standard deviation. So the sample variance is s squared, population variance is sigma squared. This last one is really important. We're going to use this quite a bit all throughout chapter 7 and 8, and that's the sample proportion versus the population proportion. Proportion is another word, remember, for percentage or a fraction. So our sample proportion, when we compute the percentage of people in our sample who think GMOs are safe to eat, for example, was 37%. The symbol we would use for that is p hat. So that's like a little caret key, p hat. And then for the population proportion, the percentage of all Americans who thought GMOs were safe to eat, for example, that's lowercase p. So we're going to use those quite a bit throughout this chapter and the next. The mean GPA of all 5,000 students at UNITA College is 2.78. A sample of 50 GPAs is calculated from this college has a mean of 2.93. So what is the population? So in this case, the population would be all 5,000 students at the college. Okay. And then the sample is the 50 that we selected. What value is the parameter? So the parameter would be the mean for the entire population. Now, this is another example where we do know the population parameter because I have access to everybody's GPAs at the college. So the population parameter in this case is the mean for the entire population. And so that was the GPA for all students was 2.78. So that would be mu in this case would be 2.78 because it's the mean for the entire population. And then the statistic, of course, is the mean for my sample. So I'm going to use X bar. And so the mean for my sample was 2.93. So make sure you're comfortable with making those distinctions. The next thing I want to talk about are biases. So all research is subject to bias of some kind. And researchers' goal, of course, is to minimize the bias as much as possible. But there's always possibilities for bias depending on a lot of different factors. There's really two in this chapter that we're going to focus on. There's others out there in research. If you go on to take a research methods class for psychology or for political science or any other major where you might have to do research down the road, there's other biases that could come up. There's a lot of them that researchers have to be aware of, but there's really three we're going to look at. So a survey method is biased, we would say. What does it mean by bias? If it has a tendency to produce untrue values or untrue results, if it has a tendency to over-represent one thing versus another, then we say the survey is biased. There are three types of biases, like I said, that we're going to look at. There's others, but there's three in this chapter that we're going to look at. The first one we're going to look at is called a measurement bias, and I'll explain what that is in a minute. The next one is called a sampling bias. The third one is using an estimator that is biased. That one's not going to come up too often in this chapter. Just be aware, though, that if you're using an estimator that came from another source that was biased, that's going to mess up your own results. Well, let's focus on these first two. So a measurement bias, it happens when the results of your survey come from asking questions that do not produce a true answer. So in other words, if they produce values or they have a tendency to record values that are not the true population value, the population parameter. When does that occur? What could cause that? So self-reported data is a good one. If you go out and ask people to respond to a survey, like let's say you ask them a question that's maybe a little bit sensitive. Maybe you asked about weight. That's something people might not be honest about. So self-reported data. So you ask everybody their weight. People may tell you a weight that's lower than what their actual weight is. And so that's going to create a measurement bias because it's going to give us an estimate for the population parameter that's not accurate. It's going to give us something in that case that's too low if people reported values are too low. So self-reported data is always a source of measurement biases, or can be a source of measurement bias. Confusing questions is another one. So asking questions that are confusing, or I must say confusing or leading questions. And I'll give you some examples of this in a minute. But if the survey question itself causes people to say an answer that's not necessarily true, or maybe causes them to lie about an answer, that's going to give us a measurement bias because more people are going to say one answer than another that maybe isn't necessarily true. And then along with questions, anything that's non-neutral. So if we ask a question in a way that, again, causes somebody to say one thing versus the other, that can cause a measurement bias. So a simple example here, this is kind of a little bit of a silly example. I'm not sure this would be something somebody would want to research, but maybe they would. A high school wants to measure how often students swear. So the administration asks teachers to keep track of how often they hear students swear in the hallways between classes. Why might this produce a measurement bias? Couple of reasons this could produce a measurement bias. It's kind of along the lines of self-reported data that students may kind of tone down their language if they see a teacher around. So we can say students may swear less near teachers. I'm not sure this is the best way to set up this survey or this research. If students know that teachers are listening in, they're probably going to tone down their language, or you speak differently around your friends than you do around your professors. Even though you're not in high school, you probably still have different language you use around different people. And so if teachers are around, they might speak differently around the teachers. So that's going to produce a measurement bias, because it's going to give us values that are lower than what they would normally otherwise be, say if the teachers weren't around. All right, let's talk about sampling bias for a second. So a sampling bias occurs when the sample that we use is not representative. So representative of the population. So it's really important that your sample actually represent the population that you're interested in. I keep thinking about COVID research, because that's just kind of been on the brain for the last couple of years. But like, think about when they did research on the vaccines. So they started out with the adult population, and they pulled samples of adults. So adults who are over 18, and that's who they did the research on. Then they did research on children from ages 12 to 18, I think, or 12 to 17. And they tested out the vaccine on children that were that age. So the idea is that the sample they were working with had to be representative of the population. If they only tested adults and then they turned around and gave the vaccine to 5-year-olds, that's a problem, because their samples would not have been representative of the population. So now they're looking at researching children that are younger before they go out and give the vaccine to children, to make sure that the sample is representative. So that's very important in research, that your sample has to represent the population that you're interested in researching. So a quick example, internet polls are very common with local news organizations. Why might internet polls produce a sampling bias? So the problem with an internet poll is that they're what we call voluntary response. If it's a voluntary response, people who tend to respond are probably very interested in that poll. So we could say that only those interested will respond. And the problem there is that that doesn't really represent the general population. If I'm not on, say, this is an internet poll on a news organization's Facebook page. If I don't follow them on their Facebook page, then I'm not necessarily going to even see the poll. So have I been represented, or has my age group or my demographic been represented? Probably not. So only those who see it online have a chance to respond. Oops, my pen quit working, hold on.